My name is Chris Harris and I'm from AlleryTutors.com, and welcome to this video on AQA Equilibria. So this is a revision video, so it's just basically a quick overview to the topic of Equilibria to make sure you've covered all or most of the bases really. Yeah, so the whole idea is literally just to go through it reasonably quickly, I suppose. The PowerPoint that I'm using here that I've made, you can, if you want a copy of the PowerPoint, and if you want to use it, you can use it for revision, print it off, and do whatever you want with it. You look at it in your own time. They are available to purchase. So if you click on the link in the description box of this video, just below, you can click on there and you'll be able to get access to it there. Like I say, this is specifically for AQA and it matches the specification, and there's the spec there. Okay, so it's it should be tailored specifically for your exam board. So there's nothing here. It's a bit stuff that you don't need to know effectively. Okay, so let's make start. So we're looking at reversible reaction because this is to do with equilibria. So this is basically where reactions go forward and backwards, and we're represented with this funny arrow here, this like backwards arrow. We'll call them like harpoons. So like two harpoons, one going forward, one going back. Here's an example. So A and B in equilibrium with C and D. Okay, so really important, some of these graphs, these can be a little bit confusing, but the forward reaction, let's look at this one here. So initially the reactants are used up pretty quickly because you've got loads of them obviously in the beaker, but then as the reactants get used up, we've got less and less and less, and they're becoming more sparse, and so the concentration over time starts to decrease. But yes, it does decrease. And going backwards, initially the backwards reaction, initially the reactants are reformed slowly, but then they speed up as the concentration of the products increase. So you can see here that the amount of product initially, when we're going backwards, starts off really quickly, and then effectively the concentrations of them start to flatten out. So this is basically the production of C and D. And equilibrium is reached basically when the amount of reactant and product is the same. This is called equilibrium. So this is when it equals the rate of the forwards reaction equals the rate of the backwards reaction. We call this a dynamic equilibrium, and the concentration of each substance remains constant. Really important, this is concentration. So don't get this confused with the amount of reactant and product. Okay, this is not the same. The amount of reactant and product, as you can see, is different. So the red line's down here and the green line's up there. It's a different amount of product. But what we're saying is that the concentrations of the substances will remain constant when it's reached equilibrium. And that's really, really important. Don't get these two confused. Okay. This only occurs in closed systems. So basically, if we had our equilibrium mixture in here, this is a reaction going on, we have to put a lid on the top of it. If I didn't put a lid on, what will happen is some of my product will escape, and basically you don't have the same concentration because equilibrium will change, as you'll see later on. So it only happens in closed systems. Right. Very important, very crucial to this is Le Chatelier's principle. Okay, so Le Chatelier, basically he developed a principle where he stated what would happen if we changed the conditions to an equilibrium reaction. Now he basically started to predict. There he is there. So he is I think he's called Henry Louis Le Chatelier, and basically he said if a reaction at equilibrium is subjected to a change in pressure, temperature or concentration, the position of the equilibrium will move to counteract that change. So this handsome chap basically came up with this idea, and a bit of a genius, I suppose, because actually he was right when he came up with this. So let's have a look at this. So if the change in condition results in equilibrium shifting to the left, we make more reactants. So if our change basically forces equilibrium to the left, we'll get more of these. Okay, these are reactants. And if it was the other way, so if the change in condition results in equilibrium shifting to the right, we'll get more product. That's basically what this Chatelier was coming up with. Now, obviously, we need to know what these changes are and how they can affect them, and we'll look at them in the next slides. Okay, so let's look at changing concentration. Okay, so remember, here's Le Chatelier's law, his principle, sorry. Okay, so you've got to remember that. So if we increase the concentration of a reactant or product, the equilibrium will shift to try and reduce the concentration. Okay, so that's important. So the opposite will happen if the concentration is decreased. So this only happens in homogeneous equilibrium. Basically, that's just reactants and products in the same state, which is fine because that's what you're going to get anyway. So if we increase the concentration of H2, okay, equilibrium will shift to the right to use it up and reduce the concentration. More NH3 will be produced. So increase the concentration of H2, there it is. So if we have more of this, the reaction will try to decrease the amount of H2 and shift to the right. And as a result, you're going to get more ammonia being produced because equilibrium is moving to use this up. And obviously, as a result, you're going to get more of this. So that's quite important. Now, if we increase the concentration of ammonia, this stuff, equilibrium will shift to the left. And using up, basically trying to do that to use up the amount of ammonia, because we've just increased it, so it'll do the opposite. As a result, we'll get more hydrogen and nitrogen produced, and that's obviously going to mean we get more reactants. So you can see here how concentration can change this. Notice all of them in the same state. That's what we mean when we see homogeneous. Okay, let's look at it in terms of change in pressure. Okay, so if we increase the pressure, the equilibrium will shift to try and reduce the pressure, and the opposite will happen if pressure is decreased. So again, this only happens in homogeneous. So let's look at an example. So if we increase the pressure, equilibrium will shift to the side with the fewest number of gas particles. This will reduce the pressure and more NH3 will be produced. So let's have a look. Increasing the pressure, it will move to the side with the fewest number of gas particles. That's the right hand side. We've only got 2 gas particles here. On the left, we've got 4. So increasing the pressure will mean we'll shift over here so you get more ammonia. Obviously, if we do the opposite, if we decrease the pressure, it will shift to the side with the most number of gas particles. This is to try and increase the pressure. So basically, we decrease the pressure, equilibrium will shift to the left because we've got more of these, more gas particles on the left. So we get more hydrogen and nitrogen gas produced. Okay. And if we change the temperature, because remember temperature can have effect on this as well. So if we increase the temperature, the equilibrium will shift to try and reduce the temperature, and the opposite will happen if temperature is decreased. This one's a little bit trickier. So what you're looking for is an enthalpy value. Okay, so if we increase the temperature, okay, equilibrium will shift in the endothermic direction, and this will reduce the temperature. So more nitrogen and more hydrogen will be produced. So let's have a look at this reaction. The forward reaction here, this one is negative. That means it's exothermic. So going forwards. So if I increase the temperature, it's going to shift in the endothermic direction because that's a reduction in temperature. So that's going backwards. So for the forward reaction is exothermic, the reverse one's got to be endothermic. So increasing the temperature will shift it in the endothermic direction to reduce the temperature. That means it moves left and we get more hydrogen and nitrogen. So this number is pretty crucial. Doing the opposite way, so if we decrease the temperature, then equilibrium will shift in the exothermic direction. This will increase the temperature and more NH3 will be produced this time. So you can see here, forward reaction, same thing is exothermic. So decreasing the temperature means Le Chatelier's principle, the temperature will increase, shift to the right to try and increase the temperature. So you produce more ammonia in this example. So that's a bit weird because actually decreasing the temperature means you get more product. Okay, which seems a bit counterproductive, but there is a problem with that, and we'll look at that in a minute, especially with this reaction. Okay, catalysts. Right, very important. Catalysts have no effect on the position of equilibrium. Okay, catalysts speed up both the forward and backwards reaction or the reverse reaction. They do that equally. Okay, so it has no effect. Really, really important. It will speed up the rate at which equilibrium is established. Okay, it has no effect on yield. Really important. Remember, catalysts have an effect on rate of reaction, but that's different to equilibria. All right. Okay. So we need to know specifically Le Chatelier's principle in terms of making ethanol. So here's the reaction. This is ethene, reacting it with water, and we form ethanol. This is an exothermic reaction. It's got minus 46 kilojoules per mole. Okay, the conditions for this: the pressure is 60 atmospheres, temperature is 300 degrees Celsius, and the catalyst we're using is phosphoric acid. Okay, so the forward reaction is exothermic. So this is going this way. So if we decrease the temperature, this will mean that equilibrium shifts to the right and we produce more ethanol. So really, we're looking for a temperature where it's quite low. Okay. So, however, the problem is the lower temperature means we get a lower rate of reaction. So this thing's going to take ages. Yes, we're going to get a good yield of this, but it's going to take us ages to do. So it's not that good, really. So basically, we come to a compromise. Okay, and the compromise is we use a temperature of 300 degrees Celsius. So the compromise is between yield and rate, how much we produce and how quickly we produce it. Okay, let's look at pressure. Now, in this reaction, a high pressure means, because remember we've got all gases here, high pressure means equilibrium shifts to the right. So if we increase the pressure, we produce more ethanol. Less moles of gas on the right, remember, so therefore Le Chatelier's principle suggests that if we increase the pressure, it will shift to the side with the fewest gas moles. That means we produce more ethanol in this case. So a high pressure increases the rate too. So this sounds pretty good, actually. Good yield and good rate. However, this is expensive. Increasing the pressure, we need thicker, more robust pipes and containers and vessels. And so actually, the compromise here is now between yield and speed and cost. And obviously, safety is quite an important one as well, but mainly cost, because it does cost a fortune to keep things under pressure. Okay. Right. We need to know about KC. Okay. Now, KC is one of these things which is one of these things that was in the old specification, it was in the A2 spec, but this has been brought down now into the year 1 specification. So this is called the equilibrium constant. You're basically given giving a value to an equilibrium reaction. So Kc can be worked out from the molar concentration in a reaction. So let's have a look at this. So the molar values in front of each species are powers in the Kc expression. So if you look here, we've got 2A reacting with B, and that's in equilibrium with 2C and D. Now the equilibrium expression, Kc, is basically products divided by reactants. Products are C and D, reactants are A and B. Look at the numbers, the molar numbers here. 2A, this turns into a power, as you can see there, look, it's A squared. So the number of moles in front of it is now a power in a Kc expression. Okay, so we've got your products and reactants. Square brackets mean concentration. Very important, it must be in concentration. We can't use moles, it's got to be concentration. So make sure the numbers you're using is concentration. Okay, so we're going to write the Kc expression, and we're going to calculate the value of Kc of the following reaction. So here we've got a concentration of SO2 is 0.4 moles per dm cubed, concentration of O2 is 0.2 moles per dm cubed, concentration of SO3 is 0.8 moles per dm cubed. Here's the reaction here. So what we're going to do is write the Kc expression. Dead easy, really. There's the expression. Kc equals SO3 squared over O2 SO2 squared. Product divided by reactants. Look at the moles, put them as powers. Okay, the calculation, dead easy. All we do, we already have concentrations, so that's fine. 0.8 is for SO2, SO3, sorry. 0.2 is for O2, 0.4 is for SO2. And you basically put your numbers in and you get a Kc of 20 in this case. Now what's important are units. So basically how we work out the units is you put the units on the top and you put the units on the bottom. Because this is concentration, this is moles per decimeters cubed. So you can see here that we have, because it's squared, we write moles per decimeters cubed twice. And we have 3 lots on the bottom. We have a moles per dm cubed there and 2 lots of moles per dm cubed there. So you can see we've written it down 3 times on the bottom. Okay, so all we do is we try and cancel them out. So cancel that out and that. And what we're left with is moles per dm cubed on the bottom. Now, when we've left with the units on the bottom, what we're going to do is flip it up onto the top. And when we do that, we just invert the little powers on the top. So instead of mole, that becomes mole to the -1. Instead of dm to the -3, that becomes dm3. So that is the units for this particular calculation. But the units can change depending on what you've got in here. So make sure you work them out properly. Okay, right. So let's look at the next bit. Now this bit's a little bit tricky. In fact, this is really tough. So you really got to try and get your head around this one. This is where we are, or the concentration of a species in equilibrium, and it can be worked out before working out Kc. Okay, so let's have a look at these ones. So we've got an example. Nitrogen dioxide decomposes according to this reaction. So we've got 2 lots of NO2, and that will produce 2 lots of NO and O2. So if we've got 33.2 grams of NO2 was heated in a vessel with a volume of 9.65 decimeters cubed at 450 degrees Celsius, and 6.8 grams of O2 were found in the equilibrium mixture. Calculate the value of Kc. Right, okay, so what we haven't got here is, normally to find Kc, we need to work out the concentrations at equilibria. Okay, now the problem is they haven't given us any of this. Okay, so we need to work it out. Now with these types of questions, it's useful to write out a table like this. I call it an ICE table. So basically we're looking for the number of moles. Moles is really important. Initial, change, and equilibria. And all we've done is we've written our reactant and products in the top rows here. Okay, so we're going to use this acronym, ICE. So what we're going to do first is we're going to say, right, how many moles do we have at the start of the reaction initially? So the moles of NO2, remember, is mass over mR. So the mass of NO2 was 33.2 divided by the mR of NO2, which is 14 plus 16 plus 16, and that gives us 0.72. Now the number of moles of product is 0 because the reaction is right at the start. We haven't produced any product yet. So we have loads of reactant, no products. Then we need to work out the change. So let's look at O2 first. So the moles of O2 at equilibrium, okay, is mass over mR. We've been told here that we had 6.88 grams of O2 were found in the equilibrium mixture. So this was after the reaction happened. So the number of moles of O2 is mass over mR, 6.88 divided by 16 plus 16. That gives us the number of moles at equilibrium to be 0.215. Okay, now you can see this is a change from 0, so we start with 0, we've now got 0.215, so that's a change of plus 0.215. Now this is going to be really, really important because this change is going to allow us to work out the rest of it. So let's go for the NO one first. So we use the molar ratio to work out the changes in other species. Remember, if we're producing products, they increase, and if we're using up reactants, remember, reactants decrease as the reaction goes. So NO, if we look at NO, this is a 1 to 2 ratio. So whereas this was a change of 0.215, this will be a change of the same but doubled because it's a 2 to 1 ratio. So the change in NO is going to be 0.430, which is double that. So 0 plus 0.430 is going to give us an equilibrium amount of 0.430. And for NO2, remember, this is a reactant, and reactants are used up. So this is going to be the same amount as this, because that's 2 to 2, but it's going to decrease by 0.430. So let's put that there. There it is. Minus 0.430, and basically we do 0.72 minus 0.430, and that's going to give us an equilibrium amount of 0.29. Okay, so what we've worked out here is the equilibrium moles of this reaction. So now what we have to do, because remember in your Kc expression is that you're looking at concentrations. So to work out the concentration of NO, we do number of moles, which is this bit here, divided by the volume. Remember, the volume of the whole thing was 9.65 decimeters cubed. So we just do that divided by that, and that gets us the concentration. We do the same for oxygen. There's the moles divided by the volume, and the same for NO2. There's the moles divided by the volume, and that gets us our concentrations. Now we have our concentrations at equilibrium. We set up our Kc expression, products over reactants, NO and oxygen divided by NO2. Put your numbers in. There's your numbers. Remember to square them. Get your answer. Your answer is 0.050. We then need to work out the units. So we put moles per dm cubed, moles per dm cubed, moles per dm cubed. We've got 3 on the top, 2 on the bottom. Get them cancelled out. There we are, and we're left with 1 unit left on the top. Because it's already on the top line, we literally transpose that, put it up there, and there's your answer. Moles per dm cubed. Kc is 0.050. Big marks here. Very, very difficult. Just make sure you write your ICE table out and make sure, remember, you're really looking for the change and use the equilibrium moles to work out the concentration. Okay, so now we're going to use Kc to find the equilibrium concentrations. So we can work out an unknown concentration at equilibrium using Kc value. So here's an example. So a reaction took place and equilibrium was established when ethanol reacts with ethanoic acid. So at equilibrium, the concentration of ethanoic acid was 1.8 moles per dm cubed and ethanol was 3.2 moles per dm cubed. The value of Kc is 3.5 at 25 degrees Celsius. What we need to do is calculate the concentrations of the products at equilibrium. Okay, so the first thing we need to do, get your expression down. So we've got all the bits in here, products over reactants. There it is there, all 1 to 1 to 1, so no powers in this one. Okay, the calculation, all we do is just substitute what we know. Okay, so we don't know these ones because that's what they're asking us to work out, the concentrations of these substances at equilibrium. We know that's 1.8, we know that's 3.2 because that's your ethanol, and then we know that the Kc is 3.5. So all we're doing is just really rearranging this. So we rearrange this expression. So these two is basically just 3.5 times by 1.8 times by 3.2. So we've just rearranged it. And basically, if I multiply all these numbers together, we get 20.16. So we know the concentrations of this and this is 20.16. Now, because we know the concentrations of these are going to be the same because they're 1 to 1 ratio, then we assume that this is basically just squared. So if we take the square root of this, we can work out the concentration of one of these. So the square root of 20.16 is 4.49 moles per dm cubed. So pretty much we have our answer. The concentration of your ester here is 4.49, and the concentration of your water is also 4.49. So you can see, pretty straightforward. A little bit of maths here, but again, just make sure that you're substituting things in the right place and you're rearranging it correctly. So what affects the value of Kc? So you need to know the effect of temperature, concentration and catalysts on the value of Kc. So temperature, Kc is only valid for one temperature. Okay, so changing the temperature will change the equilibrium concentrations and it will change Kc as well. So if I increase the temperature, the equilibrium will stay at that value until I change the temperature again. Okay, so it won't flick back, it won't alter itself. Okay, so temperature does affect Kc. Okay, so if the temperature change causes equilibrium to shift to the right, Kc will increase. If the temperature change causes equilibrium to shift to the left, the Kc will decrease. So if we have a look in this example, so in this reaction, the forward reaction is exothermic and the backward reaction is endothermic. And you can see this setup here. We know it's exothermic because the delta H is minus 197 kilojoules per mole. So if I increase the temperature in this reaction, equilibrium is going to shift in the endothermic direction. But this is to oppose the increase in temperature. So this will move backwards along here. Now, Kc will decrease. Okay, so it'll drop, it will get smaller. Okay, so if you use your Kc, if you think about your Kc ratio as like a fraction, if I decrease this value, then obviously this is going to make it smaller. Decrease of the temperature, equilibrium will shift to the right because it's moving in the exothermic direction to warm itself back up, and Kc will increase. Okay, so look, here's the expression. This is a fraction. So here's the expression for this. So the product concentration, if this increases, if I get more product, then the value of Kc will rise. Having a bigger number on here and this number remaining constant on the bottom will make this number increase. The reactant concentration increases, so these ones, either one of these, that means that obviously this over a bigger number will make this smaller, so Kc drops. So just see this a bit like a fraction really. Okay, so let's look at concentration. The value of Kc, straightforward, is unaffected by any changes in concentration. Okay, so that makes it a little bit easier. And catalysts, adding a catalyst has no effect on the value of Kc either. So basically a catalyst will speed up the forward and reverse reaction. So it doesn't have any effect on Kc. Basically, the equilibrium will be established just a little bit quicker, that's all, but it doesn't have any effect on the position or the value of Kc or the position of equilibrium. And that's it. That's the end of the Equilibria topic. I hope that was a pretty neat overview of the whole Equilibria topic for AQA. Again, if you would like to get a hold of this PowerPoint, you can purchase it. Just have a look on the description box below the video, and you can see the link there, and click on it, and you can use it to your heart's content. That's it. Bye bye.